Alright, thanks for watching, and today I want to continue our exploration of dual spaces by defining the notion of a dual basis. So previously on That's So Peyam, I defined the dual space of V, which is just a set of linear transformations from V to a field. So V star is just a space of linear transformations T from V to F. F, think of as being either real numbers or complex numbers, and those linear transformations, we call them F, like linear functionals. So a linear functional is a linear transformation from V to, let's say, the real numbers or the complex numbers. Alright, and then we also saw another miracle that, in fact, if V is finite dimensional, then V star and V, they look the same. They are isomorphic. So if dim of V is finite, then V and V star are isomorphic. Okay, and the proof just relies on noticing that V star and V have the same dimension, but if you weren't satisfied by this, I agree, I also wasn't satisfied. But it turns out there's a better way of showing they're isomorphic, which leads us to a concept called a dual basis. So for this video, assume that V is finite dimensional, and suppose we have a basis of V. So that beta be V1 up to Vn be a basis of V, and suppose F is a linear functional. F is in V star, so F goes from V to F is a linear transformation. Now look, since F is a linear transformation, remember, it's enough to determine F on basis vectors. There's this beautiful thing called the linear extension theorem, of which I have a video, that says if you know what T does on basis vectors, you know what T does on every vector. So basically, it's enough to know what F of Vi is, right? Of what F of V1 dot 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 F of Vn are. And here's a nice thing. In general, it's hard to represent linear transformations, but it turns out because the codomain is F, you can actually draw a graph of your linear transformation, of your linear functionals. Whatever that means, and in particular, you have this graphical representation. If you think of your x-axis as V, like R3 or polynomials or whatever, you have your basis vectors, V1, V2, up to Vn. Then the other axis, if you want, is the f-axis, so the r-axis, if you want. And it turns out, because it's enough to determine what f does on the basis vectors, you can plot f. So remember, f of v1, f of v2, up to f of vn, they're just numbers. So real numbers. So just draw them as dots. So f of v1, dot, 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 f of v2, f of vn. Then you get what I like to call this dot diagram, which represents precisely what f is. So given a certain diagram, you can actually recover what f is. And this diagram helps us to figure out the notion of a dual basis, because what is a basis? It's just a building block of a vector space. And it turns out any function, we can write this in terms of building blocks, which are simply the functionals, which are 1 here, 0 everywhere else, 1 here, 0 everywhere else, etc., until you get 1 here, 0 everywhere else. So here's a definition of a dual basis. If beta, let's say again, V1 up to Vn, is a basis of V, then the dual basis beta star, and again, it's a dual basis of V star, so the elements are functionals. Let's call them F1 up to Fn. Fn of V star is the set of functions, or set of functionals, Fi, simply defined by the following. Defined by, again, it's enough to know Fi on basis vectors. So if you apply Fi to the jth basis vector, you get 0 except for Vi. So it is 0 if j is not equal to I, and 1 if j equals I. And if you know this Kronecker delta thing, it's delta ij, which is precisely 1 when the indices are equal and 0 when they're not. So in terms of pictures, again, in terms of this beautiful graph that I have, well, if you have vectors v1, v2, dot, 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 let's say vi, dot, 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 vn, then what does fi look like? It's 0 everywhere. So it's 0 on v1, 0 on v2, 0 everywhere, except precisely at the ith vector, it's 1. See, and this is what fi looks like. And I know it's a little bit confusing, so let me just illustrate this like with a concrete n. So suppose you have n equals 3. Then let's see what happens. And you can almost think of it as like an indicator function of a point almost. So, so if n equals 3, let's say beta is v1, v2, v3, then the dual basis, it's f1, f2, f3. And what do those concretely look like? So if this is v1, v2, v3, then f1, it's 1 at v1, 0 at v2, 0 at v3. So this is f1, and then what about f2? Again, v1, v2, v3. f2, it's 0 at v1, 1 at v2, 0 at v3. f2. And lastly, f3, it's 0 at v1, 0 at v2, and 1 at v3. Maybe here, so 0, 0, 1. And notice those are really building blocks if you want, because in fact you may guess, and let me draw, like, grab my other picture here. If you have a general linear functional, you can actually write it as fv1 times the first f1 plus fv2 times the second f2, etc., up to fvn times the nth vn. Okay. And why is it called a dual basis? Well, you may guess. In fact, if this is a basis of V, turns out this is a basis of V star. So which is very nice. It's a very nice way of getting an explicit basis of V star. So this is V1 up to Vn, and this is, if you want, F1 up to Fn. Vn and V star. in particular, if you want to find an isomorphism, so to show they're isomorphic, just find a isomorphism that takes V1 up to F1, V2 to F2, etc., Vn to Fn. And by the way, surprisingly, this is why dual spaces are weird. It turns out you can show between V and V star, you have to go through bases to define an isomorphism. Unfortunately, there's no formula that just says f of x equals to something else without basis. So, in other words, there's no natural isomorphism between those two. All right, but anyway, this is still pretty cool. So, fact, this is what we want to show. F1 up to Fn, so this dual basis is in fact a basis of V star. And why? So, to show something is a basis, you have to show it's linearly independent and that it spans. So first of all, let's show linear independence, which means suppose you have some combination of those functions that give you the zero function. So suppose a1 f1 plus dot 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 plus an fn gives you the zero functional, basically the zero function whose value is always 0. Now look, this is an equality of functions. In particular, for every vector, if you apply this function to v, you get 0 of v, so 0. So for all v, in v, we get a1 f1 of v plus a2 f2 of v plus dot 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 plus an fn of v equals 0. The 0 vector in v. And the idea is simply choose some very smart vectors. Because look, for example, in this example, what happens when you let v equals v1? Then what you get is a1 f1 of v1 plus a2 f2 of v1 plus dot 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 plus an fn of v1 equals 0. But f1 at v1, that's 1. f2 at v1, that's 0. f3 at v1, that's 0, etc., up to fn at v1, that's 0. And what are we left with? a1 times 1 plus a2 times 0 plus an times 0 equals 0. So the only thing that's left, it's simply a1 equals 0. And by the way, so I forgot, here we're in the field, so the 0 vector is just a 0 number. So a1 is 0, and then you can just continue. If you let v equals v2, then a1 f1 at v2, which is 0, so 0, plus a2 f2 at v2, which is 1, so a2, plus a3 times f3 at v2, which is 0, plus 0, plus la la la, equals 0, and you get a2 equals 0. And then you just continue the same way, and then you get an equals 0. And that shows linear independence, because you assume some linear combo gives you the 0 functional, and you just show that all the combinations are 0. It's just a trivial combination. So it is linearly independent, and technically you are done, because a linearly independent set of precisely n vectors also spans. So this also spans, but I don't find this very rewarding. Let's actually show directly that it also spans, because then we get a really cool formula. Because you may wonder, why is this like, why do we even care about linear functionals? Because it turns out it's very easy to express linear functionals. So suppose, so f in v star is arbitrary, and we want to show that f is some linear combo of the basis vectors. Fn for some a1 up to an in f. Okay. What does that mean? So it really means we have to find this thing, a1 up to an, such that for every vector, f of x equals to f1 of x plus plus an of x. So what this means is f of x equals to a1 f1 of x plus plus an fn of x. Actually, let me use v just to be more consistent. For all v. All right, and again, we want to find the coefficients. The fi's are given, and before we continue the proof, let's do some scratch work. What should a1 up to an be, if this is even possible? So, scratch work. Well, since this is true for every v, we let v be v1, and then we get f of v1 equals a1 f1 of v1 plus a2 f2 of v1 plus plus an fn of v1. But you see, f1 at v1 is 1, and then f2 at v1 is 0, and everything else is 0 by definition of the fi's, and therefore we get a1. So reversing this, we get a1 is f of v1. And you can continue, let v be v2. Everything is 0 except the second term, and you get a2 is f of v2, etc., etc. v equals vn, an is f of vn. So if we hope that f is a linear combination of the fi's, we should let the coefficients have to be f of v1, f of v2, up to f of vn, where f is your given linear functional. So in fact, guess that f equals to f of v1, f1 plus plus f of vn, fn. But we haven't shown this. We have to show this. So in particular, let g be this. Let g be this functional that takes a vector as an input and spits out f of v1, f1 of v, plus plus f of vn, fn of v. And we have to show that g is equal to f. So now, going back to our proof. So show f equals g. All right, but very important, those are all linear functionals. So they're linear transformations. So it's enough to show that for every basis vector this is true. So enough to show f of vi equals g of vi for every vi in your basis. But then, that's not too hard to show because look, g of vi, by definition, it's f of v1, f of 1 vi, plus f of v2, f2 of vi, plus plus let's say f of vi, fi of vi, plus 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 f of vn, fn of vi. But look, what is fi? So I'm sorry, what we know then, well, f1, it's 0 everywhere except the first vector. So it's 0 at the ith vector. Let's say I is not 1 here. And same thing here, f2 of vi is 0, and then we're just left with this term, but fi is precisely 1 at vi. So that's 1. and then that's 0. So what we're left with is everything disappears except for the coefficient f of vi. But look how beautiful linear algebra is. That's exactly what we wanted to show. We wanted to show that f of vi equals g of vi. And therefore, in terms of linear transformations, they are equal. F equals g, but then g is this function by definition. So f equals to this linear combo. In particular, we have expressed f as a linear combo of our basis vectors, b star. So we are done. We have that. B star spans V star. So we have that this set is linearly independent and spans, and therefore it's a basis. And I would like to make you pay attention to this formula, because this is really what makes dual spaces so awesome. Or I guess what makes dual bases so awesome. Generally, it's hard to express a linear transformation in terms of basis vectors. But here it's saying it's actually very easy. We just have that any f in V star can be written as, or decomposed as, simply f equals to, again, because this is a basis, it's some linear combo of the building blocks. And usually the coefficients are hard to find, but now they're easy to find, because the coefficients are just, you evaluate f at the basis vectors. All right, and that's all I wanted to talk about today. Next time I'll give you an example of how to explicitly find a dual basis. So I hope you like this dual space extravaganza. If you want to see more math, please make sure to subscribe to my channel. Thank you very much.